All right, welcome back. Today I want to work a problem with you that kind of challenges our notion of conjugate beam and direct integration. So let's look at this problem. I want to find the slope at A, which is here at the pin, and the displacement at the midpoint. Now, if you look at this carefully, you'll recognize that this is a problem we worked for direct integration. So this is a pretty straightforward direct integration problem. You can see that since the load is continuous, it's easy to write that function for a moment, integrate it twice, evaluate our integration constants. Since we know the displacement at A and B, two conditions, we can get our integration constants. And then we have equations for displacement and slope, and we can just evaluate them at these points to find the solution. So let's see how that compare and contrasts with applying conjugate beam. So we might remember from conjugate beam, the first step we have to do is find the moment in the real beam. And to do that, I need to find my reaction. So I'll start here. I'll assume the shear at A, positive shear at A, and positive shear at B. And I'll just use this as my free body diagram to get started. I'll convert this load to a concentrated equivalent force. Pin's not working very well. There it goes. And that force will be the area under the curve. And it's a rectangle, so the area is simple, base times height. So that will be WL. And the centroid is right in the middle. So let me start by finding these reactions. So I'll come over here and I'll assume positive sign convention, right-hand rule, and I will sum moments about point B. So there's my equilibrium state. I'm going to sum about B to find my reaction at A. And when I do that, you'll see that this force WL creates positive moments. So the force WL times the distance of L over 2 to the centroid. And then my reaction, the shear at A, creates negative moment. So force shear at A, and the distance from B to A is L. So I find the shear at A is simply WL over 2. That shouldn't be too surprising. You notice that the total load is WL, uniform load, so you'd expect that half that, or WL over 2, be distributed to both sides. And since I just discussed that, let's go ahead and find the other one. So I'll sum forces now in the y direction. So there's my equilibrium statement for that. And then we'll do that. So I'm assuming up is positive, so shear at A is up, shear at B is down. My load WL is also down. So I can find the shear at B. When I plug my value for shear at A in here, I only have one unknown, the shear at B. And when I find that, it's negative WL over 2. Again, that makes sense too. So the reaction is up. In fact, both the reactions are equal and up to balance the applied load of WL down. Okay. So now with that information, let's draw our shear and moment diagram. So there's my template from the left edge to the right edge. And I'll begin with drawing the shear diagram. So there's my positive x-axis, positive shear. So I know from my reactions that the shear at A is going to start off at WL over 2 and end at minus WL over 2. Let's see if I can get my diagram to do that. So the change in shear from left to right, we know, is the area under the load curve, which you've already found is WL. And it's down, that's negative. So WL over 2 minus the change does bring us to WL squared over 2. So that's good. What's the shape of the curve? Well, the shape of the curve, you can see the slope of the shear diagram is the load. The load is constant. and negative. So there's my constant negative load. There's my shear diagram. Now that brings up a point here that we need to identify. I'll add that to my template. Is the area, the point where the shear goes from positive to negative. That's a point of zero shear. So what is that? Well, these two triangles are similar. So the height to the base on this one is equal to the height to the base on this one. The heights are equal, so the lengths should be equal. And those two lengths should add up to L. So this should now be L over 2. So that's an easy one. And then let's add that to our template. I'll apply positive X, positive moment. Let's see what I know about moment. Well, I know the moment at A, that's a pin, external pin, that's 0. I know the moment at B. I also know that the change in moment between any 2 points is the area under the shear diagram. So let's do that. So this is a triangle, 1/2 base times height. So that's 1/2 times L over 2 times WL over 2. So that should be W L squared half, half, half. That's 8. And what's the shape of that curve? Well, I'm going to start off with a positive slope and end with a negative slope. So I'll get a nice shape. Oop, almost missed my mark. Sorry about that. So that's half a parabola. Now the second half, from L over 2 to L, the change in moment here is this area, which is again a triangle, 1/2 base times height. This height is negative. You get the same value except negative, so that brings you back to 0. And the shape is mirrored about that center line, so I should get a shape like that. So there's my parabolic shape. Now, you might recall that a lot of our conjugate beam problems, these curves are linear. And you might even be thinking to yourself, oh no, in the next segment I've got to find areas of this. Well, for this problem, it might not be as bad as it looks. In fact, if you go into your book, those of you who have one, and look in the back of the book, you will see that the area of a parabolic section is 2/3 base times height, and then the centroid is 3/8 of that piece. So it's heavier towards the high side, 3/8. So we'll hold those in, come back and use those in just a second. So the next step is to construct our conjugate beam. So I will do that here. So looking ahead, we're going to look at our real connections and see how they map to conjugate. So we know that an external pin or roller in the conjugate space are unchanged. So my pin will stay a pin, and my roller is still a roller. What's different in the conjugate space, though, is I'm adding this moment as my load. So just take this curve and apply it to the beam as load. So there it is. Let's think about this for a second too. This load is a moment. The moment is positive, so positive load is up. And that will be the moment divided by EI. So this max value here will be WL squared over 8 EI. Okay. Now remember, one of the things we have to find is the slope at A. So the slope at A in the real beam is going to be the shear at A in the conjugate beam. So I'm going to find the shear at A here. Let's do that first. Just because this is kind of complicated to look at, I'm going to draw a simpler version of that. So here's the same geometry, except now I'm going to include my shear at A positive and my shear at B in positive. And I'm also going to include the concentrated equivalent of that load. Now remember, we wrote down before, I know the area of this parabola is 2/3 base times height. So looking at this, base is L, this is my height. So what I'm going to end up with is 2. So this 2 cancels out to make this a 4. And 4 times this will make this 12. So this should end up being WL cubed over 12 EI. And of course it happens right in the center. That's L over 2. L over 2. I'm kind of working down here. So I'm going to end up here, but I'm going to have to come back up to this area. So I'm going to go ahead and kind of squeeze down in here the solution for this part. So I'm going to start by summing moments, and I want the slope, the shear at A, because the shear at A in the conjugate beam is going to give me the slope at A in the real beam. So let's sum moments about B, make sure it's in equilibrium. So there's my statement. So let's do that. Well, about B, this load's going to create negative moment. So that's negative, and that should be WL cubed over 12 EI, that's the force, times the distance, which is middle, L over 2. And then I'm going to have minus the shear force times the distance here, which is L. So I should be able to solve for the shear at A. It looks like it's going to be negative. Just basically divide by L. So it looks like that's going to be WL cubed over 2 and 24 EI. That seems reasonable. I think that's the correct answer. Let's look at this negative. When this beam deflects, I think you can see it's going to deflect. Oops, my pin's not working very well. Something like that. And if you look carefully, you can see the slope here. That is a negative slope. The slope at B probably have the same value, be positive. But we want the slope at A, so there it is. Now to find the displacement at the midsection, I'm going to have to cut this structure right here in the middle and either look at the left side or the right side. I think the left side is going to be the best one right now because I've already got the shear at A. So I'm going to come up here and draw that. So there's my segment. That's L over 2. I'm going to go ahead and include my shear at A, which I just computed, and that's going to be acting down because it's negative. So this will be WL cubed over 24 EI. Okay, and then I'm going to have my load applied, which is half this parabolic shape, and it's acting up, and has an intensity of WL squared over 8 EI. And of course then at the cut, I've got positive shear, positive moment. And really all I want is the moment, because the moment in the conjugate beam matches to the displacement in the real beam, and that's what I want, displacement to center. I can see this looks kind of odd being up and down like this, so I'm gonna put a line in here, kind of separate this section, and I'm gonna label this. This is 1, so this is odd flow, but I'm gonna do this part first, then I'm gonna come back and do this part second. Now I need to convert this into a concentrated force F at some distance. So remember from our previous peek into the book that the area under the curve was 2/3 base times height. So in this case, that's going to be 2/3 the base, which is L over 2, times the height, which is WL squared over 8EI. And that turns into, let's see, the 2 makes that a 4. 4 times 3 is 12. Another 2 is, all those 2's cancel, so it'd be 8 times 3 is 24. So this is going to be WL cubed over 24EI. You might remember the distance from this tall end was 3/8 the base, which in our case will be 3/8. Our base is L over 2. So that ends up being 3L over 16. So you can see that's the disadvantage right now. If this thing is not a parabolic shape, if it's some segment of a parabola or some higher order curve, it might be difficult to get. This is a pretty easy one, but still, you have to know these things. And if I were to give you this on an exam, unlikely as it seems, I'd give you these formulas so that you would know them. But let's move on, see what happens. So now I'm going to sum moments at my cut shape. Make sure it's in equilibrium. And let's see what I've got here. So I've got my moment M, right-hand rule. My force is going to create negative moment. The force is going to be WL cubed over 24EI times the distance of 3L over 16. And then what do I have left? Oh, the reaction here. It's creating positive moment. I don't know if I can squeeze it in here. I'll try. So I got WL cubed over 24EI times this distance, which is L over 2. That just fits. So I sum for my moment, or solve for my moment. Let's see. So when I move this to the side, this will become positive, this will become negative. They each have a WL to the 4th over EI. So let me pull that out. So I've got WL to the 4th over EI. So what do I have left? Again, this term will go to the other side of the equation, become positive. And I got 3 over that. What's 24 times 16? Let's see. 24, 16 times 384. So this will be 3 over 384 positive. And then I'll subtract this. So that's 48. 48 goes into 384 8 times. So this becomes 8 over 384. Now the calculus is pretty simple. 3 minus 8 is minus 5. So I get minus 5 WL to the 4th over 384 EI. Okay. I remember this value. This is a pretty, the simplest supported beam is very common in structural engineering, so I do remember this as being correct. I don't remember the slope off the top of my head. One thing we can check too is the sign minus, and you would see that the midpoint does go down, so that is negative. So it looks like both the signs are right. I'm pretty sure about that one. That's the more complicated one, so I'm pretty sure the slope is also correct. So again, just to give you an idea of how the flow works, how conjugate beam can work. Very special case. The area under the moment diagram was a easy parabolic component, not a difficult one. So if you have any questions about this, email me or give me a call. And until next time, take care of yourself and be well.